The ratio test. The ratio test. The ratio test is a test for convergence or divergence of an infinite series. So we're going to let the sum of a sub n be a series. If the limit as n approaches infinity of the absolute value of the ratio a sub n plus 1 over a sub n is less than 1, then the sum of a sub n converges. If, on the other hand, this limit as n approaches infinity is greater than 1, then the sum of a sub n diverges. And if the limit as n approaches infinity of this ratio equals 1, then the ratio test is inconclusive. The sum of a sub n could either converge or diverge, so we would need to use another test to determine whether the infinite series converges or diverges. We want to note that the ratio test will tell us if a series converges or diverges, but it does not tell us what the series converges to. In this example, we're told to use the ratio test to determine whether the following series converge, diverge, or cannot be determined. So here's the first series, and as a reminder, this is the limit that we have to evaluate when applying the ratio test. So here's our generic a sub n, this is our a sub n term, and we're asked to evaluate the limit as n approaches infinity of a sub n plus 1 first, which is just substituting an n plus 1 n to each n. So let's start by saying something like, note that the limit as n approaches infinity of the absolute value of 3 to the n plus 1 over n plus 1, so that's the a sub n plus 1 part, over a sub n, which is just the general term, so over 3 to the n over n. So that's going to equal, well, now it's just a matter of evaluating this limit at infinity. So first things first, these absolute value bars, we can go ahead and drop them automatically because everything inside of here is going to be positive. We're evaluating this as from n equals 1 to infinity. So here we have an exponential, which is always positive. We're adding 1, which is still positive. So we can drop the absolute value bars. So we'll say the limit as n approaches infinity of, and now instead of dealing with a complex fraction, I'm going to, instead of divide by this fraction, I'm going to multiply by its reciprocal. So I'm going to have 3 to the n plus 1 over n plus 1 times n over 3 to the n. So just again taking that reciprocal and multiplying. So now this is the limit that I'm seeking to evaluate. And to maybe see this limit at infinity a little clearer, what its answer would be, I'm going to go ahead and apply the commutative property here. So I'm going to switch the places of the numerators and keep the n over the n plus 1. So I have the limit as n approaches infinity of n over n plus 1 times, now this 3 to the n plus 1, I'm going to keep it in the numerator over on this side though, but I'm going to rewrite it as 3 to the n times 3 to the 1 over 3 to the n. So notice 3 to the n times 3 to the 1, since they have the same base, we can add their exponent. So all I've done is rewritten this particular part, and now I can see that the 3 to the n's would cancel out. So the limit as n approaches infinity of n over n plus 1, this part is the only part that involves n, is going to be just 1. If I think about end behavior here, or horizontal asymptotes, I'm just going to have the leading coefficients 1 over 1 times 3. So the answer to this limit at infinity is positive 3. Since this value is greater than 1, the ratio test tells us that the original infinite series diverges. So we would write, so by the ratio test, the sum of n equals 1 to infinity of 3 to the n over n diverges. Now before we move on, just really quickly, we were told to use the ratio test on this example, but if I come back to the infinite series here, I could have actually applied the test for divergence. So here, if we notice, the limit as n approaches infinity of 3 to the n over n would actually equal infinity, which of course is not equal to 0. We have an exponential function on the top over a linear function, so the numerator here is going to grow bigger faster than the denominator. So since this is non-zero, the test for divergence tells us that the infinite series diverges. So we could have written something like, note that this limit is non-zero, so the infinite series diverges by the test for divergence. Let's go ahead and take a look at another example. We have the sum of n equals 0 to infinity of negative 1 to the n times 5 to the n over n factorial. Alright, so we want to go ahead and apply the ratio test. So we're going to start by saying something again like, note the limit as n approaches infinity of the absolute value of, so now we plug in n plus 1 into each n, so we're going to have negative 1 to the n plus 1, 5 to the n plus 1, over n plus 1 factorial. So that's a sub n plus 1. Now what we want to do is divide by a sub n, which is a quotient. But instead of dividing by the quotient, let's just jump straight to multiplying by its reciprocal to skip that algebra step. So we have n factorial over negative 1 to the n, 5 to the n. Alright, now let's address the absolute value bars. So the absolute value bars are going to actually eliminate for us these alternating terms. So negative 1 to the n plus 1, negative 1 to the n, those absolute value bars will allow us to ignore those terms. And everything else, 5 to the n plus 1, the n factorial, n plus 1 factorial, 5 to the n, all of that is going to be positive because we're evaluating this from 0 to infinity. And just by definition, as a reminder, 0 factorial is 1, so that's fine. So we're not doing anything we're not allowed to do there. So I'm going to go ahead and from here drop the absolute value bars as well as those alternating pieces. So I have the limit as n approaches infinity of what I have left. I'm going to do a little rearranging all at the same time. I'm going to drop the alternating parts. I'm going to put the n factorial above the n plus 1 factorial, and I'm going to write 5 to the n times 5 to the 1 over 5 to the n. So I dropped the absolute value bars along with the alternating pieces, swapped the numerators, used the commutative property, rewrote 5 to the n plus 1 like I did in the last example. So now here the 5 to the n's are going to cancel out. But we have to think about what's going to happen here. So we don't just have n over n plus 1 like the last example. We have n factorial over n plus 1 factorial. So if we think about how factorials simplify, so I'm going to go ahead and write the limit as n approaches infinity. So I do have this 5 that's here, so I'm just going to go ahead and leave the 5 in the front for now. And so if I think about what n factorial represents, so n factorial is n times n minus 1 times ... all the way down to 3 times 2 times 1. And then this is all over n plus 1 factorial. So that means I'm going to start at n plus 1, and then the next integer down would be just n, and then times n minus 1, and then times ... all the way 3 times 2 times 1. So in other words, everything n over is going to cancel out. So all of these terms are going to cancel with all of these terms, just make that a 1. So what I'm really evaluating here is the limit as n approaches infinity of 5 over n plus 1. Well, if I have a constant on the top and the denominator is getting really big, that whole fraction goes to 0. So this limit equals 0, which is less than 1. And since I have the limit as a value less than 1, the ratio test tells me that my infinite series converges. And this is what I would write as my conclusion. Now just really briefly, we wouldn't want to have to write all this out every time, so I'm just going to pull this quantity up to the top for a second and think about if I have n factorial over n plus 1 factorial, we want to be able to recognize that this is n factorial over n plus 1 times n factorial. So once I take out that n plus 1 copy, there's just n and below left. And then we can, from there, cancel these out, and I have just a 1 on top. That's how I was left with 1 over n plus 1. So we can see why it works, because we can expand by the definition of a factorial. But this is the more simplified way that we'd want to be able to write it while evaluating these limits needed for the ratio test. Let's apply the ratio test again. So we're going to go ahead and evaluate the limit as n approaches infinity of the absolute value of a sub n plus 1. I'll substitute an n plus 1 here, and an n plus 1 here will make this n plus 2, the square root of n plus 1 over n plus 2. And we will again multiply by the reciprocal instead of thinking about dividing by a sub n. So we'll have times n plus 1 over the square root of n. Now, just until we get maybe a little bit more comfortable just seeing what this limit would be without necessarily rearranging it, I will rearrange it one more time to be the limit as n approaches infinity. We'll drop the absolute value bars because everything here, if n is greater than 1, will be positive. And I'm going to switch these two numerators by the commutative property just so I can see I have n plus 1 over n plus 2. And then times the square root of n plus 1 over the square root of n. So we can maybe see it a little more clearly that this limit is actually going to equal exactly 1 after rearranging things like this, because the n behavior here is clearly going to be just 1 over 1, because we can see that the powers, the degree of each of these is just 1, so we take the leading coefficients, and the square root of n plus 1 over the square root of n is towards infinity pretty much the same function, so again we're going to end up with just the coefficient of 1. And when we end up with a 1 applying the ratio test, we get inconclusive. Essentially, the series cannot be determined by the ratio test. Now, in general, that doesn't mean that we stop. What it means is that we have to use another test. But we don't have our complete collection of tests for convergence or divergence, so we're just stuck here saying inconclusive. If you were just for a minute thinking about using the test for divergence, the test for divergence would be inconclusive as well. If I take just the regular limit as n approaches infinity of a sub n, the square root of n over n plus 1, in this case, because I have n to the first, and here I have n to the 1/2, I am going to end up with this being 0, which doesn't tell me anything in the test for divergence. It also is inconclusive. In this example, we'll go ahead and apply the ratio test again. The limit as n approaches infinity of the absolute value of a sub n plus 1. So we'll substitute an n plus 1 here. So we have n plus 1 over the quantity n plus 2 squared after substituting an n plus 1 here. And then we'll go ahead and multiply by the reciprocal. We have n plus 1 squared over n. Alright, so I'm actually not in this case going to rearrange or move anything around, because what we want to start to do is recognize what happens as n approaches infinity just overall without having to necessarily do that. So if I think about this one here, on the top, overall, I'm going to have a cubic polynomial. If I were to multiply all of this out, I'd end up with n cubed. And on the bottom, same thing. So this is n squared times an n, so I'm going to also have an n cubed. So an n cubed over an n cubed, as the limit as n approaches infinity, would just be the leading coefficients of each, and that would just be 1 over 1. So this limit, as n approaches infinity, would just be positive 1. The absolute value bars we did ignore because, again, we're substituting in values greater than 1, so all of this would be positive. So what we know is that the ratio test gives us inconclusive. Once again, the series cannot be determined by the ratio test. We're going to go ahead and apply the ratio test again. By now I'm sure you have the general idea down, so what it is at this point is just practicing evaluating these different limits and working with different looking quantities. So this one's going to be different because of the 2n minus 1 factorial. So let's go ahead and again start by evaluating the limit as n approaches infinity of the absolute value of n plus 1 squared, so we substitute an n plus 1 in here, and we'll substitute an n plus 1 in here. So if I maybe just do that scratch work to the side, I'm going to have 2 times n plus 1 minus 1. Well, that's 2n plus 2 minus 1, or 2n plus 1. And all of that is factorial. So I have over 2n plus 1 factorial. And then, instead of dividing by a sub n, we'll once again multiply by the reciprocal. So 2n minus 1 factorial over n squared. Evaluating this limit, I am going to go ahead and switch, in this case, it doesn't really matter, but I'm going to switch the numerators. So I'm going to use the commutative property. So the limit as n approaches infinity, I will drop the absolute value bars. So I'm going to have 2n minus 1 factorial over 2n plus 1 factorial times n plus 1 squared over n squared. Everything was positive, so we dropped those and then we just switched these two around. And now here, as n approaches infinity, this part right here on the right is just going to be 1. I have n squared, I have n squared, I take those leading coefficients, that part's going to be 1. So it's going to be a matter of figuring out what happens to this piece here. So 2n plus 1 is the bigger factorial. So what I want to do is think about, in the denominator here, 2n plus 1 would be the first part of expanding out this factorial, and then I would reduce by one integer, so I would go down to times 2n, and then if I reduce by one more integer by another 1, I'm going to end up with 2n minus 1. So in other words, I'm at the point where I have 2n minus 1 factorial, which is exactly the same thing in the numerator. So the numerator is 2n minus 1 factorial. And then we still do have this n plus 1 squared over n squared, and we are still evaluating a limit at infinity. But now I can see that the 2n minus 1 factorial is going to cancel out, so what I have left over here is just a 1 on the top over, on the bottom I have a 4n squared. So the bottom is going to be growing bigger faster than just the constant 1, so this overall fraction is going to go to 0. So this limit is equal to 0, which is less than 1. And the ratio tells us that that means that this series converges. And here is the formality that we would write. Let's go ahead and work out another example. So here the limit as n approaches infinity of the absolute value of plugging an n plus 1 into each of these, we're going to end up with n plus 1 squared plus 4 over 2 to the n plus 1 times the reciprocal of a sub n is 2 to the n over n squared plus 4. Since everything here is positive, we can go ahead and drop those absolute value bars and evaluate the limit as n approaches infinity of, now I'm going to go ahead and think about the n plus 1 squared plus 4 over n squared plus 4 part, separate from 2 to the n over 2 to the n times 2 to the 1. So I switched the denominators here, and then I also rewrote 2 to the n plus 1 as 2 to the n times 2 to the 1. Now, the 2 to the n's cancel, and I really just have a 1 up there. So over here I just have 1/2 left over. Now over here, as n approaches infinity, this quadratic over this quadratic is just going to end up being 1, the leading coefficient. So if I think about multiplying all of this out, I'm still just going to have n squared, and here I have n squared. So this part is 1, and over here all I have left is a 1/2. So I end up with a value of 1/2, which is less than 1. So by the ratio test, this infinite series converges. And this would be our written conclusion. In our last example for the ratio test, we have a lot of factorials going on. So we're going to be really careful when working with these factorials. We'll start with the limit as n approaches infinity of the absolute value of, in this case, if I plug in an n plus 1, I'm going to have 2 times the quantity n plus 1, which is 2n plus 2. So I have 2n plus 2 factorial over each of these n's become n plus 1. So we have n plus 1 factorial, n plus 1 factorial, times the reciprocal of a sub n factorial in the numerator over 2n factorial in the denominator. So now we're just going to be really careful when expanding these out to think about what does cancel here. So first I'm going to go ahead and drop the absolute value bars. Everything here is positive. And then I'm going to think about the 2n plus 2 factorial over the 2n factorial. And then I have n factorial over an n plus 1 factorial, and an n factorial over an n plus 1 factorial. So I'm really just kind of splitting everything up, and just keep in mind, remember, if we multiply all these back together, I still get the same numerator and the same denominator, just rearranging so that I can see the cancellations happening. So now here, 2n plus 2 factorial is the bigger value, so it's bigger than 2n by 2. So what I'm going to do is start to expand out this factorial first. So the limit as n approaches infinity, I'll have 2n plus 2, and then I'm going to drop down by an integer. I'm going to subtract 1, so I get 2n plus 1. And I'd go down one more time. If I subtract another 1, I'm going to end up with just 2n. So I've reached 2n factorial, because then it will keep going down from there, which is a factorial. And now all of this is over 2n factorial. So the 2n factorials are going to cancel out. All that's left from this first quotient is these two parts. So this is a quadratic that we have going on. But we have to see what's going to happen over here to each of these. Well, in this part, n plus 1 is the bigger factorial. It's bigger than n by exactly 1. So I'll leave the n factorial on the top, and on the bottom I'll start expanding the factorial. I have n plus 1. Then if I go down by 1, I get myself to n. And then it goes down from there, and n minus 1, etc., which is just n factorial. So these will cancel out. I end up with just a 1 on top, 1 over n plus 1. And since this is the same exact thing, I have another 1 over n plus 1. So overall, I'm going to go ahead and bring my work up here. I have the limit as n approaches infinity. In the numerator, I have 2n plus 2, 2n plus 1. And then in the denominator, I have an n plus 1 over an n plus 1. So if I were to think about multiplying these all out, what I'd have on the top is two quadratic, or on the top I'd have a quadratic, and on the bottom I'd have a quadratic. So on the top it would end up looking like 4n squared plus, I don't even have to worry about the terms that have a lower power, and then here I'd have n squared plus some other terms. The bottom line is that if I think n behavior, I end up with just the leading coefficient 4 over 1, so this is equal to 4. And since this is greater than 1, the ratio test tells us that this series diverges. And we finish writing out our conclusion. The root test. The root test is another test used to determine the convergence or divergence of an infinite series. So let the sum of a sub n be a series. If the limit as n approaches infinity of the nth root of the absolute value of a sub n is less than 1, then the infinite series converges. If that same limit is greater than 1, then the infinite series diverges. And if that limit is equal to 1, then the root test is inconclusive, and that infinite series could either converge or diverge. This is very similar, obviously, to the conclusions for the ratio test. And another similarity is that the root test will tell us if a series converges or diverges, but it does not tell us what the series converges to. In this example, we want to use the root test to determine whether the following series converge, diverge, or cannot be determined. So I'm going to go ahead and start by reminding us what limit we have to evaluate for the root test. So the limit as n approaches infinity of the nth root of the absolute value of a sub n. So here's our general term. We're going to go ahead and start out by saying, note that the limit as n approaches infinity of the nth root of the square root of the absolute value of the general term. So the absolute value of negative 1 to the n, 2 to the 3n plus 1, over n to the n in absolute value bars is what we are trying to evaluate. Well, the absolute value is going to eliminate this alternating piece. So this is the same as the limit as n approaches infinity. I'm going to go ahead and rewrite the nth root to the power of 1 over n, and I'm going to drop the absolute value and the alternating term. So I'm going to have 2 to the 3n plus 1 over n to the n, all raised to 1 over n. And now I can apply the exponent to the numerator and the denominator. So I can think about this as the limit as n approaches infinity of 2 to the 3n plus 1, and then to the 1 over n, and then the denominator is n to the n to the 1 over n. So I'm going to go ahead and bring my work up here. I have the limit as n approaches infinity of, well, here these exponents multiply, and since this in the exponent is a binomial, the 1 over n would distribute to both terms. So if I multiply 1 over n times 3n, I'm going to end up with just 3. So the numerator, so the numerator is 2 to the 3 plus 1 over n. So again, this 1 over n distributes to each of these pieces in the exponent. So that becomes 3, this becomes 1 over n. And then over, now the n and the 1 over n are going to multiply and therefore cancel and become 1, so this is just n. Now, as n approaches infinity, I have two n's here, so I want to analyze what's happening up here in the exponent. Well, if n approaches infinity in this small little rational piece, 1 over n, then that little part is going to go to 0. So the top is becoming just 2 to the third, or just a number. And then here, though, I still have this n approaching infinity, so the denominator is getting really big of the fraction. So if the top is basically just a number 8 over a really big value, this whole thing is equal to 0, which is less than 1. So the conclusion by the root test is that the original infinite series does converge. And this is the formal statement we would write to tell us that our series converges. Now, the last thing I want to mention is that how would we know to use the root test on this type of problem or this type of series? So when I see n raised to the power of n here, that's a pretty good indicator that I'm going to need to use the nth root test, because that's going to eliminate the n power, because we're going to turn the nth root into that 1 over n, which will eliminate that n in the exponent. In this example, we're told to use the root test to determine whether the series converges, diverges, or cannot yet be determined. So we have the sum of n equals 0 to infinity of this rational expression, 5n minus 3n cubed, all over 3n cubed plus 2, and all of that is raised to the nth power. We're told to use the root test for this series, but the indication that we should apply the root test is the idea that the root test involves a limit where we take the nth root, and that nth root and that nth power would cancel out. So that's how we would know that's a good test to try to determine the convergence or divergence of this series. So let's set that up. We'll start by saying something like, note the limit as n approaches infinity of the nth root and then of the absolute value of 5n minus 3n cubed all over 3n cubed plus 2 to the nth power. So again, the idea is that the nth root and the nth power cancel because we can rewrite an nth root as the power of 1 over n, and so nice things happen. We get that that root and power cancel, and then we're just evaluating the limit of a rational expression, but with absolute value bars around it. So we have absolute value 5n minus 3n cubed over 3n cubed plus 2. When evaluating a limit at infinity, if we have a rational expression, then we can think about that end behavior, the horizontal asymptote, so we can look at the dominating term in the numerator and the denominator and compare them. So in the numerator, that dominating term, the highest power term, is negative 3n cubed. On the bottom, that's positive 3n cubed. So they're both n cubed, they're both degree 3, so we can take their leading coefficients, and that's going to give us a negative 1, but it's inside those absolute value bars. So we've evaluated the limit, we're dropping the limit. The inside of this is going towards negative 1 as n approaches infinity, but it's in absolute value bars. So that means that it's positive 1. So we applied the root test and we got out exactly 1. And what that means is, by the root test anyways, this series cannot be determined. So here I'm going to put the series cannot be determined by the root test. So that means we're going to eventually learn a strategy for determining whether or not this series converges or diverges, but this is not the test that would work. It's a good try, it's what we should think about doing because of the nth power, but we get an inconclusive result. In this example, we'll again apply the root test to determine whether this series converges, diverges, or cannot be determined by this test. So we have the sum of n equals 1 to infinity of the natural log of e squared minus 1 over n, all raised to the n plus 1. We'll start by setting up our limit as n approaches infinity, and then we have the nth root of the absolute value of natural log of e squared minus 1 over n to the n plus 1. And then we have our nth root. We can think about that as to the 1 over n. So I'm going to rewrite that because this doesn't just cancel, right? The nth root and the n plus 1. So I'll rewrite the nth root. So that's going to give me the limit as n approaches infinity of the absolute value of natural log of e squared minus 1 over n. And then I'll write this as n plus 1 over n up in the exponent. So as we attempt to evaluate this limit at infinity, we'll notice that there's two different pieces that involve n. I have here 1 over n. As n approaches infinity, if the top is constant but the denominator is getting really, really big, then that overall fraction is getting closer and closer to 0. So this piece right here, that's a little arrow, is getting closer and closer to 0. And up here in the exponent, we'll think about what's happening as n approaches infinity here, well, this is a rational expression. The degrees are the same. We think about n behavior or horizontal asymptote rules. Then if the degrees are the same, we can think about that those leading coefficients. So we have just 1 over 1. So this goes, whoops, that's a highlighter. This goes to 1. And so what do we have left here? All we're going to have left is natural log of e squared, and then just to the first power, which is natural log of e squared. So evaluating this limit gives us the natural log of e squared. This part went to 0, this part went to just 1. And the absolute value bars are no longer needed because natural log of e squared is a positive value. In fact, we can simplify this further to just 2 because natural log and e are inverses. When composed like this, we can cancel these out and just get that 2. So we can form a conclusion based on the root test here. Because 2 is greater than 1, we can say that the series diverges by the root test.